Welcome to today's explainer. We are slicing open the architecture of a microchip that has completely, and I mean completely, taken over the tech world. If you've ever wondered what makes the Internet of Things actually tick, you are absolutely in the right place. We're going to bypass all the marketing fluff today and go straight to the engineering blueprint of the ESP32. It's the tiny component that's quietly running our connected lives. Now, before we get into the heavy hardware specs, think about this for a second. What connects a smart thermostat, a massive industrial robotic arm, and a life-saving medical monitor? I mean, they have vastly different requirements for speed, power, and their physical footprint, right? Well, the answer is the ESP32. Look at this incredibly diverse spread of real-world applications. The official documentation literally lists everything from smart agriculture and point-of-sale machines all the way to generic low-power data loggers. It is an absolute chameleon of a system on a chip. It just effortlessly adapts to whatever its engineers demand of it. So here is our blueprint for today. First, we'll meet the ESP32. Second, we'll dissect its brain and memory. Third, wireless communication. Fourth, sensing and control. And finally, power and security. Okay, let's jump right into Section 1, Meet the ESP32. We're starting with the physical foundation. Built by Espressif, this system on a chip uses TSMC's ultra-low power 40 nanometer technology. And 40 nanometers is really the perfect sweet spot for IoT. It's tiny enough to be highly power efficient, but it's large enough to handle high-performance radio frequency tasks. It's engineered right from the ground up to be a highly reliable 2.4 GHz Wi-Fi and Bluetooth combo chip that can actually survive in harsh RF environments. Moving along to Section 2, the brain and memory. Let's crack open the silicon and look at the core processing. You know, this isn't just a simple sensor reader. It packs some serious computational horsepower. The extensive 32-bit microprocessor inside clocks in at a blazing 240 MHz. The dual-core variant achieves a CoreMark score of over 1079. For a tiny piece of IoT silicon, scoring nearly 1080 means it can chew through highly complex mathematical and cryptographic algorithms without even breaking a sweat. Now, here is a crucial tip for when you're reading the datasheet. Pay close attention to the specific variants. While a single-core version does exist, it's strictly marked as not recommended for new designs, or NRND. The industry has definitely moved on. If you're engineering a new product today, the dual-core variant is the modern, risk-free standard you absolutely should be designing around. To feed that dual-core brain, the memory architecture is heavily optimized. It packs 448 kilobytes of ROM and a robust 520 kilobytes of SRAM for active data processing. But the real secret weapon? That's the specialized 16 kilobytes of SRAM located in the real-time clock module. As you'll see in a minute, this tiny vault of memory stays completely awake even when the rest of the chip shuts down, which is just a total game changer for battery life. All right, Section 3, Wireless Communication. Let's explore the voice and ears of this chip. On the Wi-Fi side of things, it supports standard 802.11b, G, and N protocols, with speeds up to 150 megabits per second. But its true superpower is its flexibility. It supports antenna diversity and can actually run 4 virtual Wi-Fi interfaces simultaneously. This means your device can connect to a home router while at the exact same time acting as its own access point. That's perfect for allowing users to configure the device via their phone without ever dropping the main network. And of course, it doesn't just do Wi-Fi. It packs a dual-mode Bluetooth 4.2 controller. Having both classic Bluetooth for high-bandwidth tasks like audio streaming and Bluetooth Low Energy for pinging modern ultra-low-power sensors all on the exact same piece of silicon is a massive win for reducing your overall parts cost. Let's transition to Section 4, Sensing and Controlling. This is how the chip handles physical interactions with the world around it. The secret to its physical interaction lies right in its pins. The ESP32 gives developers 34 programmable GPIO pins. You could essentially think of these as the digital hands and sensory nerve endings of the chip. Because they're highly programmable, you define exactly what each pin does based on your unique project, whether that's sending a pulse width modulation signal to spin up a motor, or just reading a simple limit switch. Mapping out its analog senses, it boasts a 12-bit analog-to-digital converter across 18 channels for really precise real-world readings, plus 2 digital-to-analog converters. Fascinatingly, it includes 10 capacitive touch sensors built right in. This lets engineers design completely smooth, totally waterproof devices that react to human touch without needing a single mechanical button. Which brings us to Section 5, Power and Security. Managing energy and protection is absolutely critical for IoT devices that might be running on a battery out in the middle of nowhere. The chip's power management unit is incredibly sophisticated. It navigates 5 distinct modes, ranging from fully active all the way down through modem sleep and light sleep. It basically allows the device to incrementally shut down functions. It's almost like a patient slowly drifting into hibernation. This dynamic control over clock frequencies and internal components aggressively saves energy. Now, here is the absolute crucial takeaway. In deep sleep mode, power consumption plummets to a microscopic 10 microamps. To put that into perspective for you, a standard little LED uses about 20,000 microamps. At just 10, the chip leaves only a tiny coprocessor and that 16 kilobytes of RTC memory awake. An ESP32 can run on a small battery for literally years, just waiting in the dark for a sensor trigger to wake up, fire off a quick Wi-Fi message, and then go right back to sleep. Of course, an internet-connected device today is just a massive liability if it isn't secure, right? Well, the ESP32 packs enterprise-grade security directly into the hardware itself. It features secure boot to ensure only trusted code runs, flash encryption to protect your intellectual property, and dedicated cryptographic accelerators for AES, SHA-2, and RSA. It secures your data in real time without ever bogging down the main processor. And our final section, Section 6, the ESP32 in action. Let's look at some real-world applications. To really ground all these abstract specs, take a look at this 2024 engineering paper on integrating the ESP32 with the MAX 3100 pulse oximeter. By leveraging the exact features we just discussed, the precise analog sensors, the dual-core processing for biometric algorithms, and the highly secure Wi-Fi baseband, engineers are building affordable, life-saving medical monitors centered entirely around this single piece of silicon. So, we've explored the architecture, the high-speed processing, the wireless capabilities, and those ultra-low power modes that make this SoC so incredibly ubiquitous. We are truly moving into an era where the boundary between the physical and digital world is dictated by 40-nanometer chips. With enterprise security and dual-core power now costing less than a cup of coffee, the question isn't whether everything will become smart. The question is, what problem will you solve when the hardware limitations just disappear? Thanks for joining me on this explainer, and keep innovating.